Okay, so 60% of the classes, and you need to have a passing grade on the assignments in order to pass the class. You will get a half a credit for finishing up this class. We are going to start today off by doing your presentations. I'm just waiting for Ethan. Where did you put what you want uploaded? Was it in Moodle, or did you send me an email? Moodle. I thought I was just there. Okay, hold on 1 second. Let me go back and see if I can see Ethan's homework. I did not see it when I was in there earlier. Give me 1 second. We're going to do our presentations first, so if there's anything that you guys need to do to get yourself ready, besides what you emailed me or sent me in Moodle, please go ahead and do. Yeah, Ethan, you didn't submit it. Maybe you didn't hit the save button. If you could email it to me or send it, actually, if you could email it to me, I guess, at this point, that would be great, because it is not in Moodle right now. So while we are waiting for Ethan to go ahead and do that, Ashley and Savannah, you guys are going to present first. I have both of your presentations here. Whoever did paper chromatography, you win. You get to go first. So what I'm looking for when you are presenting your project, I will flip through the slides or the PDF, whichever you have. I might actually. Actually, I think. Whose was paper chromatography? Ashley, was this yours or Savannah? Go ahead and raise your hand. Who did the paper chromatography? Okay, Savannah. So what I'm going to do is I'm going to give you control of the screen. And what that means is I'm going to turn my video off. You turn your video on by clicking OK if you want your video on. You do not have to turn your video on. But you should be able to move the PowerPoint by clicking the next right underneath where it says paper chromatography. So go ahead and give it a try. If it doesn't work, I'll take control back and I can move it for you. Make sure you click talk in order to talk, Savannah. And then if it's not working for you to move the PowerPoints, I'll go ahead and move them. Okay, I'm not hearing your voice come over your mic. So if you could go ahead, Savannah, at the bottom of your screen. Oh, she left. Okay, Ashley, we'll have you present first. It seems like maybe, or Savannah, if you're back. No, we can't hear you. Go ahead and try it again. I saw you logged off and logged back in. Go ahead and try again. Savannah, I was able to hear you real quick. I heard you say, "Can you hear me?" But then I lost you again. Make sure you click the talk button so that we can hear you. Okay, do you see it now? Just go ahead and click talk.
Okay, so the lab I did this week was paper chromatography, which is actually the first lab. I don't have the arrows. I don't want me to move it. Alright, so just some background about paper chromatography. It was developed by Russian scientist Mikhail Sweat in the early 1900s, and it was used to separate the green coloring in plants. It's really important in the analysis of chemical and biological specimens, and like recently some stuff it's been used for was used for the DNA analysis and identification of some victims in the 9/11 attacks. So how it works is it separates the parts of liquid or gas solutions by passing them through permeable materials. So I use chromatography paper as my permeable material. So I did the lab and I used 4 or 5 different materials. Two of them were provided, which was the copper and the bromophenol glue and the black felt pen. And then the rest I just chose a red washable marker, yellow food dye, and blue gel pen. And what I had to do was make marks on a piece of chromatography paper, and then I would soak it in water to see how far the parts of it traveled in the molecules. So I found that the copper and the bromophenol blue traveled 82 millimeters, and when I added the potassium iodide to show the copper, it traveled farther, and so that was the 82 millimeters, and the 79 millimeters was the actual bromophenol blue, which you can see in the picture. Then the black felt pen actually traveled all the way to the top. If you can see, it's the really bright blue one that has multiple colors, so it traveled all the way 100 millimeters. The red washable marker traveled 74 millimeters, the yellow food dye traveled 89 millimeters, and the blue gel pen traveled 85 millimeters. Okay, and then just like some observations, but like what I noticed was that the red washable marker and the black felt pen had like the most noticeable like observations, because all the others were just normal, but like the red washable was only one color, and it moved the like least amount, and it only moved 74 millimeters, while like the black felt pen had the most colors. It had 5 different colors, and it moved the farthest, and it went like over actually, because I had a paper underneath the chromatography paper, which is 100 millimeters. So the copper moved farther than the bromophenol blue in the same amount of time, and copper has a mass of 63.54 moles, and it's smaller than bromophenol blue. So in chromatography, the smaller molecules move faster, and while the large molecules move more slowly, and they're left behind because they can't fit as well through the porous material. So that's why the copper moved farther in the amount of time as the bromophenol blue. And that's what I have.
All right, great job, Savannah. That's a neat lab, and Savannah, picked a couple of different pens and markers in order to do it. Excuse me, in order to do the lab with. You can also do it with different types of food colorings or different types of foods. Foods that are rich in color. Spinach is one you can use, and it will pull out the different colors of the foods. So great job working on that, Savannah. Perfect. Okay, Ashley, you are going to go ahead and go next. Ashley did a PDF, so I just have to switch. Alrighty, here we go. Ashley, I will flip the page when you need to. I changed the number of pages on yours so I could make the text bigger. Alright, so go ahead.
Okay, I did lab number 6, which was oxidization and reduction. And here's what I wrote. During this past week, I did a lab on the oxidation and reduction reactions with a few metals. Firstly, though, I had to learn what oxidation and reduction was. Oxidation is when a reaction causes an atom to lose electrons to another atom. On the other hand, reduction is a reaction that causes electrons to be gained by an atom from another. They go hand in hand during the reaction. One atom will lose electrons and be oxidized, achieving a more positive charge. The other will gain electrons and be reduced to a more negative charge. This all takes place in a common chemical reaction called single replacement reactions. As this experiment shows with metals, a more reactive metal will take the place of a less reactive metal. In my lab, I used copper nitrate, iron nitrate, zinc nitrate, sandpaper, copper metal, iron metal, zinc metal, and a 96-well reaction plate. First, I put 5 drops of copper nitrate in wells A1, D1, and G1 of the first column in my reaction plate. I continued to put 5 drops of iron nitrate in A4, D4, and G4, and 5 drops of zinc nitrate in A7, D7, and G7. The next step was to make sure that the metal had no coatings on them so that the bare metal would be exposed. I used my sandpaper to rub off anything that might get in the way of my results. Then I put a piece of copper in wells A1, A4, and A7, a piece of iron in D1, D4, and D7, and a piece of zinc in G1, G4, and G7. By spreading the metals out across the reaction plate, I prevented them from touching each other and causing any difference in my results. The reaction took a few minutes, but when I looked back, I could clearly see which metals were affected. The copper metals and iron metals were not very reactive metals in this experiment. They were not oxidized by any of the 3 chemicals. However, the zinc metal reacted to both copper nitrate and iron nitrate. I filled this information into a table, clearly representing the data, as shown there, with the metals and solutions on the left, and then showing how each solution of metal was affected when they were put together. According to the results that I got, iron and copper metals were not oxidized. Therefore, the solutions they were in were not reduced. The zinc metal was oxidized, and the solution it was paired with were reduced in the reactions. Let's look at the zinc metal and copper nitrate. The zinc metal turned a dark purple when it was placed in that solution, which was a clear indication that reaction had taken place. The equation for this oxidation-reduction reaction is seen below, which it was the zinc plus the copper nitrate, and it was the reaction caused the copper and zinc to displace each other and switch. So it's copper and then like zinc nitrate. In this situation, the oxidizing agent is the copper nitrate and the reducing agent is the zinc metal. We could apply these same basic principles for the zinc metal and iron nitrate. After completing the lab, I decided to do some research on the different metals to see how my results compared to those of others with similar experiments. The only difference I found between my results and that of others was my iron metal and copper nitrate. Most others said that when the iron nails are put into a copper nitrate solution, the iron should displace the copper, and the copper should oxidize the iron, causing some rust. I did not see this happen with mine, so I decided to try again with iron and copper nitrate. My second try, I was able to observe the reaction, and I made the proper changes to my table in row 2, as shown below. where I changed it so that the iron and copper nitrate showed a reaction instead of a non-reaction. These differences may have been due to many reasons and mistakes I could have made. For example, the iron might not have been clean enough so the metal was not fully exposed, or I might not have given the iron metal long enough to react with the copper nitrate the first time. However, after trial and error, I was able to come to the conclusion that iron metal can be oxidized by copper nitrate. This experiment serves as a way to learn about chemical reactions. It allowed me to observe oxidation and reduction reactions of metal, and understand how the movement of electrons causes what I saw. Also, this lab showed the different levels of reactivity in metals, and I was able to compare how they all worked as opposed to other. Now I know how a single replacement reaction works, and I can try to identify it in the world around me.
All right, great job, Ashley. Thank you very much. One of the reasons that I do this, and we're going to do the same activity again at the end of the year, where you are going to pick a lab and do it, is because I feel like it gives you guys a great way to pick something in this class or in the lab book that we're not going to have an opportunity to do as a class, but that you are interested in. So Savannah picked the paper chromatography. Ashley picked the oxidation reduction reactions. Great job. Cami is going to present next week. I have her lab that she sent me, and Ethan is having trouble sending his, so he is going to send it to me right after class, and he is going to present it next week as well. Okay, so this week I said we are not doing any labs. Unfortunately, we are going to do some chemistry. We are going to do some balancing equations after we talk about a few different elements. I know you guys have all seen the periodic table before. We worked with the periodic table last week. This week we are going to look at the periodic table in a little bit more depth, and we are going to learn a little bit more about where an element is situated on the table and why that is important. So, let's take a look at your PowerPoint screen. Right now, you guys should see the periodic table on it. Does anyone know what, actually, we're going to go over to our whiteboard. I just unlocked it for each of you. And we are going to, what do you know about the periodic table? Last week we talked a little bit about atomic mass, atomic number, and what they mean. But what else do you know about the periodic table? I'm going to put up here something. I'm going to put that where an element is located tells us about its electrons. Tell me what you know about the periodic table. What can you add up here? I want to see what you know about the periodic table. All right, Savannah, hold on. Let me refresh it. Can you see it now? Okay, Savannah, maybe I just shut my video off. Sometimes that speeds things up. But maybe if you logged out and then logged back in, I'm thinking maybe when you got kicked out earlier, maybe it didn't connect completely. So log out and log back in and see if that helps, and we'll keep brainstorming right here on our whiteboard. All right, Savannah, are you able to see the whiteboard now? Awesome. Okay, and I unlocked your whiteboard, so see if you can add anything up there. Okay, I'm going to give you guys... Oh. Okay, when I read it, we'll go over it. If you repeat something, that's okay, Savannah. Okay, I'm going to give you guys 2 more minutes. All right, perfect. Okay, so the periodic table is a tool scientists use. So let's see what you guys know or think you know about the periodic table so that I know how much in depth we need to go. So let's take a look. I'm going to start over at the left. Group effort of multiple scientists to create an order. Moseley, Newland, and Mendeleev, the most notable. Periods are rows and groups are the columns. Different groupings are alkali metals, alkaline earth metals, halogens, transitional metals, lanthanides, actinides, metalloids, and semi-metals and noble gases. The higher the atomic number, the more particles. Great job. Radon is poisonous because its core is too heavy. Lead is the heaviest element without being radioactive. The first column of atoms is dangerous because they throw particles at you. If there isn't an even amount of electrons, then the element is poisonous unless it joins with another atom. I'm not sure about that one. It may be true, but I have never really thought about it. As you go down the periodic table, the electronegativity decreases, and going to the right, it increases. The higher the atomic number, the more particles an atom has. Noble gases don't like to bond because they have full valence shells. You can usually tell how many electrons are in valence shells of an atom has by what group it's in. Group 1 is 1 electron, 2 is 2 electrons. But you skip transition metals and go to group 13 for 3 electrons. Okay, well you guys know and have a great basis for the periodic table. We're going to look at a PowerPoint that I have about the periodic table. However, I'm going to do some skipping around. So you're going to have to bear with me a little here. Here is a periodic table. Okay, you guys have seen them. No, does not matter what type of periodic table you have. They're all the same. So here we go. Science has come a long way since Aristotle's theory of air, water, fire, and earth as the 4 basic elements. Scientists have identified 90 naturally occurring elements and have created about 28 others. Elements alone or in combinations make up our bodies, our world, the sun, and in fact everything in the entire universe. The most abundant element in the Earth's crust is oxygen. What I have right here is I went ahead and I made a pie graph. Well, I borrowed a pie graph of the elements in the Earth's crust. So go ahead and take a look at them. They probably are mostly the ones you would have guessed. So the periodic table organizes elements in a particular way. A great deal of information about an element can be gathered just from where it is on the periodic table. For example, you can predict with reasonably good accuracy the physical and chemical properties of an element. You can also predict what other elements a particular element will react with chemically. Understanding the organization and plan of the periodic table will help you obtain basic information about each of the 118 known elements. This part we talked about last week, so we're going to fly through these. Go ahead, Ethan.
If you could find a black door, would that contain the elements from the supposed island of stability?
I'm sorry, I didn't really hear you. All I heard was if you could find a black door. So if you could repeat that.
if you could find a black door, would that contain elements from the supposed island of stability?
I have no idea. I'm not really sure. So the periodic table looks like this. However, it has the names of the elements in it. But if you were just to look at it, we have blues are all metals, greens are all nonmetals, and metalloids are all purple. A metalloid is something that has metallic and nonmetallic characteristics or properties. So here are some properties of metals. Metals are very good conductors of heat and electricity. Metals are shiny. Metals are ductile, which means they can be stretched into very thin wires. Metals are malleable, which means they can be pounded into thin sheets. And the chemical property of metal is reacts with water and can cause corrosion. Properties of nonmetals. Nonmetals are poor conductors of heat. Nonmetals are not ductile or malleable. Solid nonmetals are brittle and easy to break. They are dull, and many nonmetals are gases. Properties of metalloids. Metalloids means metal-like, and they have properties of both metals and nonmetals. They are solids that can be shiny or dull. They conduct heat and electricity better than nonmetals, but not as well as metals. They are ductile and malleable. Elements in the periodic table are also grouped into families, which are columns. The up and down columns on a periodic table. Elements in a family have similar properties. They're also categorized in rows. Elements in rows are called periods. Elements in period, similar properties. So go ahead and take a look. Does anyone want to volunteer to read this slide for me? Go ahead, Ethan.
Family. Columns of elements are groups or families. Elements in each family have similar but not identical properties. For example, lithium, Li, Na, potassium, K, and other members of the family Ia are C metals. All elements in a family have the same number of valence electrons. Periods. Each horizontal row of elements is called a period. The elements in a period are not alike in properties. In fact, the properties change greatly across even given row. The first element in a period is always an extremely active solid. The last element in a period is always an inactive gas.
Thank you very much. We are going to fly through some of these. Okay. Any volunteers, someone other than Ethan, want to read about hydrogen? Go ahead, Ashley.
Hydrogen. The hydrogen square sits atop family A1. but it is not a member of that family. Hydrogen is in a class of its own. It's a gas at room temperature. It has one proton and one electron in its one and only energy level. Hydrogen only needs 2 electrons to fill up its valence shell. Do you want me to keep going?
Sure, you can go ahead and read this one too. Go ahead.
The alkali family is found in the first column of the periodic table. Atoms of the alkali metals have a single electron in their outermost level. In other words, 1 valence electron. They are shiny, have the consistency of clay, and are easily cut with a knife.
Thank you very much. Okay, now the alkali metals are located where it is highlighted yellow in the periodic table. Alkali metals are also the most reactive metals. They react violently with water. Alkali metals are never found as free elements in nature. They're always bonded with another element. Okay, so what does it mean to be reactive? Well, when we describe elements according to their reactivity today, elements that are reactive bond easily with other elements to make compounds. Some elements are only found in nature bonded with other elements. So what makes an element reactive? An incomplete valence electron level. All atoms except for hydrogen want to have 8 electrons in their very outermost energy level. This is called the rule of octets. Atoms bond until this level is complete. Atoms with few valence electrons lose them during bonding, and atoms with 6, 7, or 8 electrons gain electrons during bonding. So here you have sodium and chlorine. Sodium has 1 valence electron. Chlorine has 7 valence electrons. They are going to join together. Very good question. Why is it called an octet? It's called an octet because ideally there would be 8 electrons in that last shell. So what happens is sodium loses 1 electron and chlorine gains that electron. And then you would have sodium chloride. So here we have a couple slides about alkaline earth metals. Would anyone like to read this one for me? Or this couple? Go ahead, Savannah.
Alkaline earth metals. They are never found uncombined in nature. They have 2 valence electrons. Alkaline earth metals include magnesium and calcium, among others. Continue.
Oh, go ahead, Savannah. Sorry, you're going to have to hit the talk button again. But go ahead, you can read this one too.
Transition metals. Transition elements include those elements in the B families. They are the metals you are probably most familiar with: copper, tin, zinc, iron, nickel, gold, and silver. They are good conductors of heat and electricity. Transition metals again. The compounds of metals are usually brightly colored and are often used to color paints. Transition elements have 1 or 2 valence electrons, which they lose when they form bonds with other atoms. Some transition elements can lose electrons in their next to outermost level. Transition elements have properties similar to one another and to other metals, but their properties do not fit with those of any other family. Many transition metals combine chemically with oxygen to form compounds called oxides.
All right, thank you very much, Savannah. Boron family. The boron family is named after the first element in the family. So the top element in the boron family is boron. Atoms in this family have 3 valence electrons. This family includes a metalloid, boron, and the rest are all metals. This family also includes the most abundant metal in the Earth's crust, which is aluminum. The next group is the next family is the carbon family. Anyone want to volunteer to read this? Go ahead, Ethan.
Family. Atoms of this family have 4 valence electrons. This family includes a nonmetal, carbon, metalloids, and metals. The element carbon is called the basis of life. There is an entire branch of chemistry devoted to carbon compounds called organic chemistry.
Go ahead. You can read the next couple of families, Ethan.
The nitrogen family. The nitrogen family is named after the element that makes up 78% of our atmosphere, metalloids and metals. Atoms in the nitrogen family have 5 valence electrons. They tend to share electrons when they bond. Other elements in this family are phosphorus, arsenic, antimony, and bismuth. Oxygen. Atoms of this family have 6 valence electrons. Most elements in this family are protons. Oxygen is the most abundant element in the Earth's crust. It is extremely active and combines with almost all elements. Halogen. The elements in this family are fluorine, chlorine, bromine, iodine, and acetylene. Halogens have 7 valence electrons, which explains why they are the most active nonmetals. They are never found free in nature. Halogen atoms only need to gain 1 electron to fill their outermost energy level.
All right. Thank you very much, Ethan. Okay, and the last one is the noble gas family. Noble gases are colorless gases that are extremely unreactive, all the way on the right-hand side of our periodic table. One important property of a noble gas is that their inactivity. They are inactive because their outermost energy level is full. Because they do not readily combine with other elements to form compounds, the noble gases are called inert. The family of noble gases includes helium, neon, argon, krypton, xenon, and radon. All the noble gases are found in small amounts in the Earth's atmosphere. There are 30 rare elements composed of the lanthanide and actinide series. Those are the ones on the bottom here in the blue, the ones that are set apart from the periodic table. One of the elements in the lanthanide series and most of the elements in the actinide series are called transuranium, which means synthetic or man-made. Okay, this is just the... All right, so that's where we're going to stop with the periodic table and learning about the periodic table. What we are going to focus on now is how you actually balance a chemical equation. Now, I would like you guys to kind of gauge yourselves. How familiar are you with balancing chemical equations? I want you to rate yourself 1 to 5. 1 means great, or 1 means poor, 5 means Great, you can do it in your sleep. Okay, I'm going to, oh, you don't have to do it there, Ethan. I'm going to send a poll to you guys. Okay, 1 means you're not that good at it. 3 means you can, you're halfway decent. 5 means you can get any one that I give you, no questions asked. How do you think you are at balancing equations? Okay, we are going to look at how we balance equations, and we are going to use something, a chart, to help us balance equations. So if you look up on your PowerPoint screen right now, and we are going to practice a whole bunch. The conservation of mass means that everything on one side of an equation is equal to everything on the other side. Just like if you were doing a simple algebra equation. If you're doing a simple algebra equation and you have x plus 1 equals 2, you have to find that other x, and it would be 1. 1 plus 1 equals 2. What's on the left-hand side of the equation is equal to what's on the right-hand side of the equation. That's what we are going to do today with chemical equations. It's a little bit harder with chemical equations, but I think once you get used to using this table, you will be surprised at how easily it comes to you. So, if a chemical equation does not obey the law of conservation of mass, the equation is said to be what? And the answer is not balanced. So if the left-hand side is not equal to the right-hand side, then it's not balanced. So let's look at the steps we need to take to balance chemical equations. Now my suggestion to you would be to take a piece of paper and kind of work with me through these. Okay, so write down Fe plus O2. And that arrow is yields. Yields Fe2O3. So basically, we want the Fe plus O2 to equal the Fe2O3. And we're going to take a look at how we do that. We are going to make what I call a wrap table. A wrap table is a chart with 3 columns. The first column is the number of atoms in the reactant. That's the left-hand side of the equation. The center column is the atom. And the right-hand column is the number of products. Easy enough. And if you look at my paper, I have it written out just the same way he does here. Now the first thing I'm going to do is write down my atoms. So in this equation, I have 2 atoms. I have Fe, which is iron, and I have oxygen. So they go in my center column. Now I need to figure out how many atoms of that I have in the reactant and how many I have in the product. It's fairly simple to do this. To find the number of atoms, you are going to take the coefficient, which is the number before our symbol. So for Fe, there is no number, so we assume it's a 1. Just like if there is no number in front of an x in an algebra equation, you assume it's a 1. And you are going to multiply it by whatever the subscript is. So for Fe, there is no subscript. So 1 times 1 is 1, which is where they got the 1 under the R column. Now we look at oxygen. There's nothing as the subscript, so that means it's a 1. And, as the coefficient. And the subscript is a 2. 2 times 1 is 2. That is how they got the number of reactants for oxygen to be 2. Now we look at the product side. The product side, we have no number as the coefficient, so that means it's a number 1. So 1 times the subscript 2 is 2, and 1 times the subscript 3 is 3. So now we have our wrap table completed. This table is showing us what atoms are present in this reaction, how many there are, and if they're reactants or products. To balance this equation, we need to have the number of reactants of iron be equal to the number of products iron. So we need that 1 to be equal to 2, and we need the 2 to be equal to 3. We are going to do that by adding coefficients. When we're adding coefficients, you can only multiply. Okay? Go ahead and let me know if you are understanding this. Send me either a smiley face or a little frown face. Yes, I get this, or I've lost you already. Okay. So what we need to do is we need to try and balance this equation. Now work with me on this one. Try to follow me. It'll make more sense the more of these that we do. Now we look back at our equation that we have written on our paper, and I am going to multiply the iron or the Fe atoms in the reactant times 2. So I'm going to add a 2 as the coefficient in front of the Fe, the iron, and that is changing my number of reactant atoms to 2. Okay, and if you look at right here, I modify my equation by putting the yellow 2 in front of the iron atom. Now I'm going to update my wrap table. And I'm going to look at it, and I'm going to think in my head, are all of the atoms in my wrap table balanced? They're not. My iron atoms are balanced now, but my oxygen atoms are not. I need to figure this out because I need a balanced equation. I need everything balanced. So I'm going to move to the next unbalanced atom. Now, how can I balance oxygen? I need to figure out what coefficient I can put in front of the O2 and the Fe2O3 to make my oxygens equal. I'm going to put a 3 in front of the O2 in the reactants and a 2 in front of the Fe2O3 in the product. So now my equation looks like the equation on the bottom. 2Fe plus 3O2 yields 2Fe2O3. And I'm going to update my number of oxygen atoms in my reactant and my product. But, bad news. Something else happened. Since I added that coefficient in front of the Fe2O3, I also need to multiply the coefficient 2 times the subscript 2 of the Fe. So I have to change my number of Fe, or iron, atoms to 4 in the product. So now I have that. And now I need to balance my iron. So I need to have 4 reactants, 4 atoms of iron in my reactant. So I'm going to cross off my 2 in front of the Fe, and I'm going to change it to a 4. And I'm going to update my wrap table. And now I look at my table and my equation again. And do I have a balanced equation? Yes, I did. Ethan, how did I turn the iron into an hour like that? I'm not sure what you mean by that. How did I turn it into a 4? Okay. I changed it into a 4 because I now, on my reactant side, it was a 2. So that only gave me 2 atoms of Fe. But on my product side, I had 4 Fe. So I had to figure out what times 1, because my subscript was a 1, equals 4. And 1 times 4 is 4, so my coefficient became a 4. We are going to look at our whiteboard now, and we are going to do one together. You do not need to be sorry by any means. Okay, I'm going to put one up here. We're going to work through it together. All right. So here is my equation. I'm going to put it in red so it's easy for us to pick out. Please don't write in red. Okay, now I'm going to write my subscripts. So there is my equation. Now I am going to make a wrap table. And I have my number in the reactants. I have my atom. And I have my number of products. So my atoms are going to be S, E, and O. And now I need to use that and figure out if my equation is balanced. So let's write this on your paper and try to work it out along with me. So how many, oops, and I forgot one. Down here I need my chlorine. Okay, how many SEs do I have in the reactant side? there's no coefficient here. I'm going to draw a line everywhere I can put a coefficient. There's no coefficient. So that is 1 times 1 is 1. How many oxygen atoms do I have on my reactant side? There's not a coefficient here, so we make it 1 times 2 is 2. And there is no coefficient in front of the chlorine, so 1 times 6 is 6. I'm going to send you a poll. Okay, do you understand how I got the number of reactants? Go ahead and answer it yes or no. Nope. Doesn't seem to be sending. Write in the text chat yes or no. Do you understand how I got the number of reactants? Okay. Now I want you to, on your piece of paper, figure out how I got the number of products. Remember, you're taking the coefficient, which in both cases is 1, and multiplying it by the subscript. You are taking the coefficient, which is 1 in every case, and multiplying it by the subscript. Okay, so Ashley, can you go ahead and fill in on the whiteboard the number of reactants you got? Oh, yes, I do. I'm sorry, products. Yes. Awesome. That is exactly right. So right now, the SCs are balanced, the O's or the oxygens are balanced, and the Cl's are not balanced. So I need to figure out one thing to start. I need to figure out how to make this 2 in the product side equal to the 6 on the reactant side. Well, what are you going to multiply 2 by to get 6? What times 2 is 6? Think back to our math facts and we think 3. 3 times 2 is 6. So we are going to take and put a coefficient of 3 in front of the chlorine on the reactant side. That changes this to 6. And we cross the 2 out. This 3 being right in front of the chlorine does not change the number of Se or O atoms in the product side. So, a proper balanced equation would be SeCl6 plus O2 yields SCO2 plus 3Cl2. Does that make sense? No matter how long your equation is or how complex it looks, you are going to do the exact same thing. Let's try another one. Okay, so here we go. Let me find another simple one. Okay. Now we are going to do the same thing. I have to add my subscripts because I can't add them as I'm typing, so give me a second. We are looking for the correct coefficients to fill into the green blanks that I'm drawing. Do this on your paper with a wrap table, please. One thing to think about while we are doing this is you are only using multiplication. You are not adding anything. So I'm going to make my wrap table. Up here, you guys make it on your papers, please. Now what you should be doing is you should be looking at the coefficient in front of the SnO2. You see that there is no number there, which means it is a 1. And after the Sn, there is no subscript. The subscript is after the O, or after the oxygen. So 1 times 1 is 1. 1 times 2 is 2. Now we look at the hydrogen. There is no coefficient, which means it is a 1. And the subscript is 2. 1 times 2 is 2. So go ahead and do the product side. Okay, so we are going to go ahead and we are going to look at our products. There is no coefficient in front of the Sn, which means it's a 1. There is no subscript after the Sn, which means it is 1. 1 times 1 is 1. Now we look at the H2O for water. There is no coefficient in front of the hydrogen. 1, the subscript is 2. 1 times 2 is 2. Oops, down here. Now we look at the oxygen. There is no subscript, which means it's a 1. And there is no coefficient, which means it's a 1. 1 times 1 gives us 1. So let's take a look and see, is there anything unbalanced? Oh, I see something that's unbalanced. The oxygen right now is unbalanced. We have a 2 in the reactants, and we have a 1 in the product. So we have to try to balance the oxygens. Now, how are we going to get a 2 in the product side? Go ahead and turn your mic on. How are we going to get a 2 in the oxygen on the product side?
Give oxygen a coefficient of 2, so that it's 1 times 2, which equals the reactant.
Awesome. So we need to get a coefficient of 2. So we are going to put a 2 right up here as the coefficient. So 2, the hydrogen's in there too, so that's going to change the number of products of hydrogen. 2 times 2 makes this a 4. 2 times 1, 2 times 1 makes this a 2. So we have our oxygens balanced now. However, now our hydrogen is not balanced. How are we going to get that hydrogen balanced? Ashley, how do you think?
You you get the hydrogen on the reactant side, you times that by 2, so that's a coefficient of 2.
Awesome. We are going to put a 2 here as the coefficient on the reactant side. 2 times 2 is 4. Now everything is balanced, so now we have a balanced equation. Check. Good job. Okay, we are going to try one more. Okay, while I'm writing this one up on the board, you can go ahead and keep looking at this equation if you have any questions. Okay, I want you to try to do this one all on your own. Okay, when you're doing these, something to keep in mind is you cannot take numbers out. You can only add numbers in. So you can't take a coefficient or a subscript out. You can only put numbers in, and you can only put coefficients in the blank spots that I just put up here. Okay, Ethan had a good question. How would you do the hydrogen? Well, let's look at our reactants. We have 1K. For oxygen, we have an oxygen in the first part of the reactant and the second part of the reactant. So first we figure out here we have 1 coefficient and 1 for the subscript, so we have 1. And we are going to add, because the plus, the second coefficient. So we have 1 as the coefficient here, plus 4 as the subscript. So 1 plus 4. For hydrogen, there's a 1 as the coefficient and a 1 as the subscript. 1 times 1 is 1, plus 3 times 1 is 3. And the P is 1. Now we go ahead and look over at our products. 1 for the coefficient times 3 is 3. 1 for the coefficient for P times 1 for the subscript of P is 1. Oops. P is down there. For the oxygen on the product side, we have 4 for the subscript times 1, so we have 4, plus 1 for the coefficient times 1 for the subscript, plus 1. And for hydrogen, we have 1 times 2 is 2. So we need to balance our K's and our H's. So let's first try to do the K's. Let's add a 3 here. So this is going to change this to a 3. It's going to change this. No, I took into account the H3, Ethan. I have 1 for the 1 times 1, and then 1 times 3 is 3. So now I have K for 3, and I have to figure out my oxygen. So I have 3 plus 4 is 7. And now that changes my hydrogens too, and I have 3 hydrogens. So I'm going to kind of make this a little neater, and I'm going to write that as 7, write that as 6, and I'm going to write this as 5. So now my K's are balanced, but my oxygen and my hydrogens are not balanced. So I need to figure this out. I'm going to try to balance my hydrogens first. So in order to get 6 hydrogens, if I have a 2 as the subscript, I need to make the coefficient a 3. 3 times 2 is 6. 3 times 1 is 3. So now instead of 5, I'm going to have 4 plus 3, which equals 7. And now I have a completely balanced equation. Balancing equations are very difficult. We are going to work on balancing equations again next week. Your homework this week does not have any equations to balance on it. Your homework this week is to pick any element that you would like. And you are going to write 3 to 5 paragraphs about your element. The specifics are on the Moodle site. I want you to submit it on the Moodle site It should be by 9 a.m. Eastern Time. That way I have enough time to grade it before class. If you have any questions, certainly feel free to email me or call me. We are going to do a lab again next week. I would also like you to read the lab before you get to class. Okay, if you have any questions, I will be here. Otherwise, I hope you guys have a great day, and I will see you all next week.